Okay, differentiability. This is the last part of 3.1 and all of 3.2. So if f prime of x exists everywhere, exists at any x value, then we say that the function is differentiable. So in other words, if you can find the derivative at any point on a function, then it is differentiable. A function that is differentiable at every point is a differentiable function. And what if it's on a closed interval? Then all you need to do is check the limits, and as long as those circles are closed at the endpoints, then we say that it is differentiable on the closed interval from a to b. Right? So if I have, let's make sure this works. And if I have a function that just stops, okay, it just stops right here, and it is open. We'll call that A and that B. Okay. Then it would not be differentiable at A, and it would be differentiable at B. So it would be differentiable on the interval soft bracket A up to B, hard bracket on B. Differentiable on that interval. Okay. Next. How might f prime of A fail? Let me try to make this a little bigger. That's good. Well, there could be a corner. I lost my pen. There could be a corner. So it could be like our absolute value of x function. Zoom in. That didn't work. Okay. Create like our absolute value of x function. So it just has a corner. Let's do something like this. Okay. We say that the derivative does not exist at this point right here. So therefore that is a point that is not differentiable. Okay. In other words, the left-hand derivative is not equal to the right-hand derivative. So from the left, the slope is -1, and from the right, the slope is +1. So therefore, at that point right there, then it fails to have a derivative. A cusp is very similar, only that's our little bird function. So like x to the 2/3, for example, as one of our fundamental functions. X to the 2/3. It has a cusp right here. A cusp meaning that if you were to do the secant lines, right, from the left-hand side and from the right-hand side, in one direction it would be going to -infinity, it would be a vertical line, and then this direction it would be going to +infinity, almost a vertical line, right? So because one's positive and one's negative, then we call it a cusp. And at that point, then the derivative does not exist. A little bit different than that one. Vertical tangent, again, very similar to before, only they're going to be the slopes of the secant lines are going to approach both positive or both negative infinity from the left and from the right. So here's our example, which is x to the 1/3. And from the left, right, my secant lines are approaching a slope of +1, and from the right, it is still +1. Okay? And if I had negative x to the 1/3, then they would both be approaching negative infinity, still be a vertical tangent, and therefore it is not differentiable at that point. Discontinuity, well, let's say that the y values are actually different from the left and from the right. Then, of course, the derivative wouldn't exist. So from the left, there's my y value. From the right, there's my y value. Obviously, we're not going to have a derivative existing at this point right here because we can't even agree on a y value. Okay, it's not even continuous. Next example, show that this function is not differentiable at 1. So first of all, we need to check whether or not it is continuous. So if I look from the left, okay, I would get f of 1 would be 1 squared plus 3 times 1, so that's 4. Okay. And from the other side, I have 3 times 1, which is 3, minus 2 equals 1. So therefore, this is not differentiable at 1 because my function is discontinuous at 1. Okay. So show that it is not differentiable since f of x is not continuous at x equals 1. At x equals 1, it is also not differentiable. And I'll also say what the actual y values would be from the left and from the right. T-I-A-B-L-E. Okay. The limit from as x goes to 1 from the left, I would follow my x is less than or equal to 1 function and then plug it into this one. So I have 1 squared plus 3 times 1, which is 1 plus 3, which is 4. It's not equal to the limit as x goes to 1 from the right, as we already showed, because then we would plug it into the second part of the function, second piece of my piecewise function, 3 times 1 minus 2 equals 1. Since those two are not equal, then the function is not continuous. Therefore, it cannot be differentiable. Of course, we cannot find a derivative or the slope when the y values aren't even equal to one another. Let's say that the y values were equal to one another. Does that necessarily mean that the function is differentiable? No, it still does not, right? Then, if that was the case, we would have to find the derivative from either side and see if the slopes were the same. Okay, if I had a function like this, and then my piecewise functions meet right there, and then my slopes are different from the left and from the right, then I would get a corner, and therefore it would not be differentiable. Okay, but if it just happened to be that this function left off at that slope, and then my new function continued on as a straight line, and it just happened to have the same slope right here, then it would be differentiable. So say one curved up like this, and the other one curved down like this. Absolutely fine as long as the slopes are the same right there. Okay, so from the left, it would be called my left-hand derivative is 2x plus 3. Like I said before, because this was discontinuous, you wouldn't have to do it for this example. I just want to make sure you understand. And then from the right, it is 3. And then I would plug in 1. And from the left, the slope would be 5. And from the right, the slope would be 3. So therefore, since 5 is not equal to 3, again, it would be a corner if the function was in fact continuous and the limits were the same. Okay, all differentiable functions are locally linear, meaning if we zoom in very close to a point on a function, it will start to resemble the tangent line at that point. So I have a little example. So here is some cubic function that I just made up that goes to the origin. And what I would like to do is zoom in on this function. So if I start zooming in, then what we should notice is that it slowly becomes a straight line, right? And if I go far enough in, even if I was at a place where, it doesn't look like it's going to straighten out, if it's differentiable, then it will eventually look like a straight line, and that line is your tangent line. Okay? I didn't graph the tangent line with it because it would be the exact same line at this point, and you wouldn't even be able to tell the difference. Okay, and you get the point. So, connection between differentiable and continuous functions. If a function is differentiable, then it is continuous. But you cannot necessarily go the other way. Just because it's continuous does not mean that it is differentiable. Okay? Obviously, we have continuous functions that have points where they're differentiable, not differentiable, because those are our examples in the beginning, right? Such as absolute value of x, right? That's a continuous function, but yet it is not differentiable at x equals 0. Going back to the top, if f has a derivative at x equals a, then f is continuous at that point. Differentiable functions are always continuous, and like I said, we can go one direction, not the other. Just like all squares are rectangles, but not all rectangles are squares. Example, for which values of x does this function fail to be continuous, and where does it fail to be differentiable? Okay, it fails to be continuous wherever the limits from the left and from the right are not equal to one another. Okay, all these points seem fine. The only points I need to ever check look like 1 and 4 and 5. So as far as continuity goes, from the left, as I go to 1, it's approaching 0, and also from the right, it's approaching 0. So that's fine. As I go to 4, from the left, it's approaching, I don't know, some high number, and from the right, it's approaching, I don't know, some lower number. So therefore, at 4, it fails to be continuous. And then at 5, right, it is approaching the same y values from the left and from the right, so that is fine too. But differentiable, okay, well, of course, 4, because as soon as we know that it's not continuous, then it can't be differentiable there. And also here and here, right? Here we have our jump discontinuity. So therefore it is not differentiable. Here we have a corner. Here we have another corner. So at 1 and 4 and 5. My function's not differentiable. At 1, right, the slope from the left-hand side is negative, the slope from the right-hand side is positive, so there's no way those could be equal. Same thing at 4, at 5, I mean. From the left, you have a positive slope, and from the right, you have a negative slope, so there's no way that those are going to be equal, okay, if they're not even the same sign. And last thing is the intermediate value theorem for derivatives. If a and b are 2 points on an interval on which f is differentiable, which is very, very important, okay, you have to make sure that that holds, then f prime takes on every value between f prime of a and f prime of b. So, in other words, if you know what the derivative is at one point and you know what it is at another point, then it has to have every single derivative in between those, just like your other intermediate value theorem from before. They're just specifically saying that, oh, by the way, you can do the same thing with derivatives. So the last example says, explain why this function must have a horizontal tangent at some point x equals c in its domain. So at some place, we have to have a slope of 0. Well, if I can find a place where my slope is positive and another place where my slope is negative, then since that function is differentiable, since it's a polynomial, and all polynomials are continuous and differentiable, then then by my intermediate value theorem, I can say that it must take on every slope that's between those two values, the negative and the positive, so therefore it must have a point where the slope is equal to 0. So how are we going to do this? Let's think about what this function is going to look like. I'm going to factor it. We're going to see what we get. This one actually factors really easily. Okay. This tells me the zeros of my function. It tells me at positive 3 and at negative 1, my function is 0. And since my leading coefficient is positive, then it is opening up. So it looks like this. Okay. And of course, we know that the vertex is going to be halfway in between these two. And instead of finding the vertex, though, I can just find the slope at negative 1, which is a negative number, and the slope at 3, which is a positive number. Therefore, somewhere between negative 1 and 3, there must be a point where the slope is 0. So let's find the slope at negative 1. First, we need the derivative of the function, and that is easy. So we just get 2x minus 2, because it's just our power rule. And I want to find my slope at negative 1. So I just plug negative 1 into that function, and I get negative 2 minus 2 is negative 4. And then my slope at 3 should just be the positive of that. So at 3, I get 2 times 3 is 6, minus 2 is 4. Good. Since it's symmetric, right, across the axis of symmetry, okay, then these two slopes are just opposites of one another, opposite signs. So if I have the slope at negative 1 is negative 4 and the slope at 3 is 4, positive 4, then therefore there exists a C between oops, between -1 and 3, such that f prime of c equals 0. Therefore, giving us a horizontal tangent line. Okay, and that is it for the notes for today. And you just have a few questions for homework, and I will see you in class tomorrow.